When user base explodes, the central monolithic database takes the brunt of the impact. Under that massive, continuous load, the system starts to crack. The traditional response is vertical scaling, buying a server with more RAM, CPUs, and bigger drives. But hardware has physical limits, and buying the most powerful server becomes a financial impossibility. To survive, you have to stop trying to build a bigger machine. You must break the database apart and distribute the load across smaller commodity servers. You absolutely have to fragment your data. The dilemma is how to slice data. Do you cut by rows, separating the individual records, or cut by columns, separating the unique attributes? This choice dictates whether your system survives a massive traffic spike or crashes entirely during a complex analytical report. This diagram shows horizontal partitioning. We slice the table directly across its rows, moving complete records onto distinct server blocks. Alternatively, vertical partitioning slices downward. We separate specific columns, isolating those attributes into freestanding blocks. These two strategies solve completely opposite bottlenecks. One is built for transactional volume, and the other is built for analytical read speed. Moving a massive volume of complete individual records quickly requires a totally different architecture than scanning a single attribute across millions of historical records to find a trend. Picking the wrong fragmentation strategy for your specific bottleneck will actively degrade performance and introduce massive technical debt. Horizontal partitioning is commonly known in the industry as sharding. It distributes your complete rows across multiple machines in a cluster, which are called shards. A shard key controls the traffic. The database inspects a specific value in each incoming row, like a user ID, routing it to a specific server. This provides infinite linear scalability. If traffic doubles, you simply add identical servers to absorb the load. This makes horizontal sharding ideal for online transaction processing, IoT telemetry, and massive user applications prioritizing the ingestion of continuous volumes of complete records. But there is a severe trade-off. Problems start the moment an application needs to query data that spans across multiple different shards. If you need to generate a complex report, separate servers now have to communicate over the network to stitch records together. Cross-shard joins introduce massive network latency, turning a simple query into an engineering nightmare. Horizontal sharding buys you infinite write capacity, but heavily penalizes complex, multi-record relational aggregations. Vertical partitioning, utilized in column-oriented stores or highly normalized snowflake schemas, takes the opposite approach. Watch this diagram as a traditional row block morphs into a column layout. The system physically organizes data on the disk by attributes, isolating identical data types into sequential disk clusters. This layout creates extreme efficiency for online analytical processing. When an analytical query finds an average salary, it skips straight to the exact sequential block. It bypasses irrelevant data like names, saving massive memory. The penalty for this speed comes when you need to reassemble a single complete record. To serve a user profile, the database must jump to multiple physical disk locations just to rebuild that one row. Vertical partitioning provides lightning-fast analytical reads, but makes pulling or writing a single complete record highly expensive and slow. Beyond read speeds, vertical partitioning offers a massive secondary advantage: extreme data compression efficiency. This diagram demonstrates what happens when you group identical data types together. Compression algorithms run incredibly efficiently over a sequential block of integers or dates, shrinking the storage footprint dramatically. And if a value is missing, the column layout simply omits it. This completely avoids the physical storage waste associated with empty, null values that plague traditional relational rows. The physical storage footprint shrinks, but leveraging it means you have to abandon traditional row-level database insert commands in favor of batch loading your data. This matrix evaluates both architectures side by side to make the trade-offs clear. For the storage layout, horizontal relies on row-based network distribution. Vertical relies on column-based sequential disk isolation. For their optimal use cases, horizontal handles OLTP and high write volumes. Vertical dominates OLAP and large-scale aggregations. And the catch? Horizontal introduces cross-shard join latency. Vertical introduces expensive single record assembly. Choosing an architecture is an exercise in mapping your database's physical storage layout directly to the application's single most frequent action. This flowchart maps the final decision path. You start by identifying your primary systemic bottleneck. If your bottleneck is massive user traffic, transactional volume, or IoT ingestion, you route definitively to horizontal partitioning or sharding. If your bottleneck is data warehousing and running complex financial reports across millions of rows, you route to vertical partitioning or columnar stores. Do not mix these up. If you attempt to run complex business intelligence reports across a horizontally sharded database, the network latency of pulling fragments from 50 different servers will stall your system. And if you use a vertically fragmented database for high-frequency transactional updates, the constant disk rewrites across multiple columns will destroy your performance. System survival requires choosing the exact tool engineered for your specific bottleneck.